My name is Joshua Harris, and this is my presentation on neural networks. So, for a brief introduction here, that's where we're going to start with this discussion, and then we're going to move into more of a brief history that, this technology has kind of been incorporated throughout time. And then we'll kind of take a quick look at kind of a simple example and implementation of neural networks. And then we'll really finish up with the way these are kind of being implemented in today's technology. So to start, we will take a look at what really is a neural network. So a neural network is simply a system that took inspiration from the way our brain works, our biological neural networks. And these systems that we create, they learn to perform the tasks given to them after exposure to certain data sets, and then they will take these data sets without any type of task or algorithm that we've specifically assigned to them to solve that information. Now, the idea is that these systems generate those characteristics from the data that's been passed to them without, again, any pre-programmed understanding of what that data set is. Now, how exactly would they be useful to us? So, neural networks really give us the ability to solve real life and real world situations that are a little too complex for us to naturally comprehend. They can take these relationships between the inputs that we give them, and they don't have to be linear, and they can be extremely complex. And they can utilize those to make generalizations or certain inferences that will reveal those deeper relationships and patterns to make certain predictions. Now, they also can take really complex and volatile data with things that have extremely high variance, and they can utilize those to predict events that are extremely rare. Such as things that we see with financial data, stock information, markets, things of that nature. Now, kind of moving along here, we're going to take a look back in time and get a brief history of the way neural networks kind of came about in their infantile stage. As well as how it's kind of progressed and come a bit in and out of relevance over the last 70 or so years. So where things really got started was with a neuroscientist, Warren McCullough, and Walter Pitts, who was a mathematician. They wrote this paper on how neurons might actually work in our brains, and they modeled a simple neurological network with these electronical circuits. And then comes along Donald Hebb. He proposes that these pathways strengthen over time. That is to say, they have this plasticity about them. And that's really the basis that these neural networks are built on. There are two major concepts that really predated the idea of neural networks, and that would be the concept of threshold logic, which is to say that converting this continuous input will then leads to a discrete output. And then there's also Hebbian learning, which is a model of learning based off of that neuroplasticity. Now, with those concepts in mind, comes along Rosenblatt. He proposes what was to be known as the Mark I perceptron, and this really used a simple decision process where each neuron took in an input, and then it converts that to a weighted sum. So there, in that node, there's already a weighted value to it. And then what it will return to us is an output of 0 or 1. And if that sum was below the threshold, it would return that 0 to us. And if it was above the threshold, it would return a 1. Now the weights that would be used, and that's what the neural network is learning on, is based off of the successful inputs and predictions. So as we take a look at this timeline, as things kind of progressed, he was working on the perceptron, and then the Dartmouth Summer Research Project, where it was an AI. It boosted both artificial intelligence and neural networks. And then what really comes along is the first application to solve a real world problem. So the creation of the Adeline and Madeline system, actually which is still used even up into this day, was a system designated to eliminate the noise in phone lines. And again, that's still a system that we use to this day. And again, progressing along our timeline here, we see that as the successes grew, as more came about with this research, naturally so did the hype behind the research, as well as the inevitability of the hysteria behind it as well. So there were some accounts of many people saying that computers would eventually take over all jobs that did require any type of human thinking. For instance, there was an example of a machine being built that translated Russian manuscripts, and they said that over time, in the next 5 to 10 years after that came about, that all translators would eventually be rendered useless. Of course, we did see that that did not come to happen. Now, again, though there was hype behind it, of course, there was hysteria. So there were many people saying that eventually robots would take over. This would become so smart that it would no longer be necessary for humans to actually have any jobs, even up to the point where they had conjecture of humans marrying robots. But things really came to a head and an end for that kind of period when Minsky and Papert released a paper conclusively arguing that Rosenblatt's approach could not effectively be translated to multi-layered neural networks. And after this research, the entire field was stunted for a period of time. I think it was about 10 to 15 years where we really didn't see any progression in that field, mainly because research funds really dried up. Now, as we take a look here, what really caused the resurgence was Japan announcing their 5th generation efforts that really got the US going, and they started refunding research into this field. And we can see that many meetings and assemblies were created from then on out. A neural network was created even towards the late 90s. And even up until now, we're seeing the growth of this technology in many industries. So now that we've kind of gotten a quick overview of the history of neural networks, let's now kind of take a look at how does this system actually work. And we're going to be taking a look at a really simple, really basic implementation of a neural network, and it's going to be doing some image processing. So this example here, we're going to be trying to decipher the number that is given in our picture off here to the right. So each one of those pixels in that really awkward looking 9 that we see there, it's represented by a 28 by 28 grid, and each pixel represents either a 0 or 1 in between that range, depending on the shade of that pixel. And that is going to be the initial value that we feed to our first set of nodes, that input. So for all of those 28 by 28 pixels, we'll have 784 initial starting nodes, all of them with the value of the shade of that particular pixel. Now each one of those will perform a calculation, and it's going to decide whether or not it's above or below that threshold, may include some type of bias. And once we have arrived at that number, we will send that information to the next node in the layer. Now, as you can see, we do have 2 layers in between our initial nodes and our final output. Those are what we call hidden layers. Now, there's a concept known as deep learning. Really, the deep in that phrase represents how many hidden layers and how many layers we have between the initial input and the output line. So as we move on, after the initial nodes have sent their information to the next layer, that layer will also perform nodes, and this will continue on until we reach our final output layer. And as you can see, we have 9 nodes in that layer, and our prediction will come based off of the brightest, or the node there with the highest number. Now, without getting too in-depth, we will start to see that the way the system will work is it will start to recognize patterns and each one of those based off of their weights. And in a perfect world, our final layer will only have to really recognize any of those patterns and combine those patterns, and that will give us the output that we are looking for. Now again, this is just a simplified example, but we can really start to see how intricate the design of these neural networks really can get. And now that we've really kind of touched on and taken a look at a simple example here, let's really just kind of discuss the current applications and where we're really seeing this in today's world. So as we just looked at with image recognition, again, taking in that image input and outputting what exactly it is. So if we fed it, a picture of a lion or a tree, our neural network would be able to decipher that image and let us know what it thinks that image is. Now again, that's not the only place where we're seeing things happen with these neural networks. So for instance, banks are using this to detect credit card fraud. They're getting an influx of their customers, and then they will say whether or not that a transaction took place, whether they were actually there for the transaction. And furthermore, we're seeing this especially in the medical field and disease diagnosis. So we're seeing where these neural networks are able to predict even better than physicians based off of the input that we're giving them. Now, we are obviously restricted by having the ability to give these neural networks all possible permutations of the way that disease can appear. But that's something that we learn over time, and therefore these systems can be better with the information that we give them. But that's not really the only place. We're seeing this in so many fields. One of particular interest is the uses of self-driving cars to be able to detect the images along your car, allowing it to sustain its movement without hitting a pedestrian or another car. Improved even in other markets, such as the actual business world, we can see this used to improve stock prediction. Again, we kind of touched on its ability to kind of eliminate and guess better with those volatile data sets. But one thing to definitely keep in mind with neural networks is they're obviously not perfect systems. Overconfidence in those neural networks can truly lead to costly mistakes if they are implemented incorrectly, or if we make incorrect assumptions about the data or the way the system works and it's outputting those predictions. And with that, that's really my presentation that I have for you today. As we can see, I do have some references that I have accumulated here. If you want some more information, I highly suggest taking a look at my references here. And that is my presentation on neural networks. Thank you.